Hello and welcome to this next section uh, on an introduction to RF microelectronics. In the previous section, we discussed some core principles where we talked about units, we talked about convergence, we talked about time variance, and linearity. This was a brief discussion. Now, in this section, we'll focus on non-linearity in RF systems and how to characterize non-linearity or how to quantify non-linearity in RF systems, and we'll see the impact of non-linearity on the performance of RF systems. Now, this section will be divided into certain subsections. To start with, we'll talk about harmonic distortion, and then we'll see some effects like gain compression, intermodulation and cross modulation, and then we'll see how nonlinearity exhibits itself in a cascaded system. For example, if we have one system and it has certain nonlinearities, and then we have another system, it has some nonlinearities, then if we have a combined system, then what will be the nonlinearity of this combined system in terms of the nonlinearity of the constituent systems. So we'll see how nonlinearity scales in cascaded stages. And in the end, we'll see how nonlinearity impacts modulation schemes. And this is again a very important topic. And this is a practical topic when it comes to real life RF designs. So let's start. Now, to start with, we have to understand where nonlinearity comes from, at least mathematically. So mathematically, if I have a function y, say y of t is a function of x of t, right? So this system, so y of t is a function of x of t. This system is linear as long as f of a times x of t is e times y of t. So the system must follow this. The system must follow scaling. So if I scale the input, the output should scale by the same amount. 2, if I have as an input, if I have x1t plus b x2t, right? And each of these x1 and x2, they follow the same, say for example, same behavior. So x1t would give y1t and x2t would give y2t. Then a scaled combination of these should be equal to a y1t plus b y2t. If the system behaves in this manner, then we call this system linear. Okay, now where does non-linearity come, and where does the name come from? So it's simple. If I have y equals a times x of t, if I just plot this, then it would be a straight line. So it's a linear system. Now, when is it not linear? It's not linear if I have non-unity exponents on top, right? So if I have a x1 x raised to power 1, which is x, basically xt, plus some coefficient b x squared t. Now, as soon as this squared term comes in, now this system is not linear, right? So this system is not linear. We can go on adding these components. Now we can generalize this and we can express, so if we can express it in this way. We can say y of t is alpha 1 x of t plus alpha 2 x of t squared plus alpha 3 x of t cube plus so on and so forth. So this is the general equation of a nonlinear system, where alpha 1, alpha 2, alpha 3, these are coefficients for the different powers of xt, which is the input. So this is the input and this is your output. Now, we talked about in the overview or in the introductory slides, we talked about why we love sinusoids, right? Because we can replicate any other system if we understand the behavior of a system to a sinusoid. So now what we'll do is that we'll treat this x1t as a sinusoid. We'll say that this x1t is a cos omega t, right? Once we do that, then we have this relation. And obviously there will be plus dot dot dot. But in this case, for example, we consider just 3 up to a third order system. And so we'll have an output y of t, which is alpha 1 times, this is nothing but x of t, and this is nothing but x squared of t, this is x cube of t or xt cubed, xt squared, so on and so forth. Now if you expand these terms, if you expand the cubes and the squares and the fourths and the fifths, if you go on expanding them, you'll get something like this. You'll get a relation. Now this has been expanded up to the third order. You'll get a relation something like this. Let me clear the screen so you can see it clearly. Now what you'll get is, you will get a term which is independent of frequency, right? Then you'll get a term which is a coefficient, right? It's a coefficient, it's a scaling factor for the fundamental frequency omega, right? It's the same frequency of the input. So if I have a system y and I provide a function x, right, and x of t, and x of t is a cos omega t, right? The input is x of t, and on the spectrum it is just one frequency omega, but the output has a lot of things. The output has a component omega, the output has another component with a frequency of 2 omega. So if I look at the output, I have a component at omega, I have a component at 0 which is DC, right? I have a component at 0, I have a component at omega, I have another component at 2 omega, 3 omega. Now this is a third order system, that's why we are limiting ourselves to 3 omega. It can go on and go forth, and you can have many other components. Now to simplify things, we just take it up to the third order, and as you can see, you have this term. This term is the coefficient for the second harmonic, and this term is the coefficient for the third harmonic, 3 times the frequency. So a non-linear system, so this is a non-linear system. A non-linear system is also able to generate harmonics from a given single tone signal. Now you should distinguish this from the previous case, which was a linear system. That linear system was able to generate harmonics because of time variance, but this is different. The system is able to generate harmonics because this is inherently nonlinear. Okay. Now let's look at some points which we can gather from this. So first of all, this distortion, that is the generation of these extra harmonics, right, which were not present in the input signal, this distortion is called harmonic distortion. So now we have a distortion in which extra harmonics have been created. Okay. Okay. So what can we understand from this? We can understand some terms. So what is alpha 1? Now alpha 1, if a is small, that is if I have x of t, which is the input signal, right? If it's the input signal and a is the amplitude of this input signal. Now if a is very small, right? If a is very small, then a cube, right? A cube will be extremely small. A cube will be extremely small and we can neglect this term, right? And similarly, a squared and a cube and so on and so forth, these will be very small terms, and what we'll be left with is y of t is equal to alpha 1 times a cos omega t. So this is what we'll get if a is very small. Now what is a cos omega t? It's nothing but xt. So y of t is equal to alpha times x of t. Sorry, alpha 1 times. So alpha 1 is nothing but the small signal gain of the system, right? If you have a which is very small, then you can ignore all of these terms, and what you're left with is this simple relation, and what that implies is that alpha 1 is simply the small signal gain of the system. Let's clear that out. So alpha 1 is nothing but the small signal gain of the system, and at the fundamental frequency, right, the coefficient or the gain, the overall gain at the fundamental frequency is not just the small signal gain. There's another term which is 3 alpha 3 times a cube by 4. So the gain at fundamental frequency is alpha 1a plus 3 alpha 3 a cubed by 4. So this is your gain at the fundamental frequency, and if a is very small, then it boils down to alpha 1. The gain boils down to alpha 1. Now, okay, this is actually wrong. So this is not the gain at fundamental frequency, this is the coefficient. The gain would be alpha 1 plus 3 alpha 3a squared by 4. Right? So you take this alpha out, so a cos omega t, and then you take this out, this becomes squared, and then this one becomes your x of t. Then what remains is the gain, right? So the gain at fundamental, the coefficient is this, but the gain would be this term would be your gain at fundamental frequency. Okay, let's look at some more observations which we can gather from this. Now what we see is that the input did not have any DC, right? There was no zero frequency component, but the output has a DC component, and it comes from this alpha 2 terms, the alpha 2 term. And if we expand this this expression to higher order terms, as I mentioned, it's restricted to the third order. If we move on to higher order terms, we'll see that there will be more terms like plus alpha 4 a raised to power 4 by 4 or something like that, right? You'll have more terms like this, but all of these even terms, they will contribute to a DC offset. So when you look at this DC offset, it is contributed by the even order terms. Okay. Oops. Okay. Yeah. So all the even order nonlinearity terms, they introduce these DC offset. So you may see a system, y of t. You may supply a signal x of t without any DC offset, right? And you might see that the output, instead of this, now the output has a certain DC offset. What this implies is that this DC offset is because of the even order nonlinearities. Okay, so this system has some even order nonlinearities, and those even order nonlinearities, they contribute to this DC offset in the output. Now once we know that, we can start to act about this. That's exactly what we do when we deal with differential systems. So in differential systems, the system has an odd symmetry. So what that means is that if you have a function, now in a differential system, what you do is you take a function y plus minus y minus, right? So this is how differential systems work. And y plus is nothing but it's a function of, say, xt is a function of xt. Y minus is a function of minus xt, right? So these are out of phase. That's how differential systems work. Now if you look at y plus minus y minus, let's assume this is your y, and your y plus would be and this, this is xt, right? So your y plus would be alpha 1 xt plus alpha 2 xt squared plus alpha 3 xt cubed, right? What would y minus t would be minus alpha 1 xt, right? And plus alpha 2 xt squared, right? Because the square would make that plus, again, minus alpha 3 xt cube, right? So if you subtract the two, you'll see that these terms will cancel out. So you will have, let me clear the screen and write this again. You'll have y plus is equal to alpha 1 x1 plus alpha 2 x1 squared plus alpha 3 x1 cube. You'll have y minus equals minus alpha 1 x1 plus alpha 2 x1 squared minus alpha 3 x1 cube. Now when you subtract the two, you will have y plus minus y minus equals twice alpha 1 x1, and this cancels when you subtract the two, right? So this cancels and you'll have plus twice alpha 3 x1 cube, so on and so forth. So in differential systems, you don't have these even order terms, and when you don't have these even order terms, you don't have this nonlinearity. So in a differential system, you will not find DC offsets. Okay. Yeah. And practically, harmonic distortion is not a big issue, because if you're working at a certain frequency, say for example GSM, right, you're working at 800 megahertz, Then the harmonic distortion would be when components are generated which are harmonics of this. So the next component, the second harmonic, would be 1600 megahertz. Now the thing is that GSM receivers, they are built around 800 megahertz. So the first stage of any GSM receiver, so if it's a GSM receiver, the first stage would be a filter, right? Which would filter anything above and anything below 800 megahertz, that would be filtered out. So practically speaking, harmonic distortion does not impact the performance of RF circuits, but at the same time it's an important mechanism which should be understood. And then it's also important to understand because it forms the base of other distortions which have practical significance. Okay. Let's look at an example of how harmonic distortion can lead to other problems which might be of practical importance. Let's assume we have a system. It's a mixer, and a mixer multiplies two signals, right? So you have y of t, which is a product of x1t and x2t. And the question is, you have this mixer, it multiplies two signals and then it scales them by a factor k. Okay. Now assume x1t is a1 cos omega 1t and x2t is a2 cos omega 2t. If the mixer is ideal, determine the output frequency components. Okay. If you multiply these two, then we know from basic trigonometry, we'll have two components, omega 1 plus omega 2, omega 1 minus omega 2. So if I have the system, it has x1t, it has x2t, it has yt. Now x1t is at omega 1, x2t is at omega 2, then y1t is at, it has two components, one at omega 1 plus omega 2 and one at omega 1 minus omega 2. So again, the system is non-linear because yt has components which are not present in the input signal. None of these components is present in the input signals. It's a completely different spectrum than the input spectrum. So yt is definitely non-linear. Now this is how the system should behave. This is the ideal behavior of the system. If I supply two signals at frequencies omega 1 plus at frequencies omega 1 and omega 2, then the ideal switch should give me two signals at the output. Not two signals, but a single signal with two frequency components at the output, one frequency component at omega 1 plus omega 2 and the other frequency component at omega 1 minus omega 2. Okay, now let's see what happens if, let me clear the screen. Now let's see what happens if one of the signals, say for example x2t, suffers from a third order non-linearity. Now what's a third order non-linearity? We looked at it before. Now third order non-linearities, if you have a third order nonlinear system, you'll have a third order non-linearity would be something like this. A component with 3 times the frequency and an amplitude of alpha 3 times a cubed by 4. Okay. So now it says that x2t now x2t, earlier it was a2 cos omega 2t. Now it's not just that, it's also some non-linear term which is there in the signal, And this can come due to a number of reasons. It can either be due to the antenna, or the transmitting station was nonlinear. That's why there was another term which was added to this. So there are many things which can lead to this. So now we have yt. Again, it's a mixer, so this will be x1t and x2t now. So this is x2t. X2t is not just an omega 2t term, there's also a 3 omega 2t term. Now we have the system, which is y. Let's not call this y. Y is the output. Okay. Now we have a system. So at the input we have two signals. One is at omega 1. Earlier the other one was just omega 2, but now it is omega 2, and there's also a 3 omega 2 term. Okay, that is being supplied to this. Now what will the output look like? Okay, now if we do the maths, if we supply a signal which has a third order nonlinearity, and then we do the multiplication, we find a lot of new frequency components. So the output has a component at omega 1 plus omega 2. This is just like earlier. The component at omega 1 minus omega 2, again this was normal. Now these two are the desired signals, right? This is what we expected if the switch was ideal. We expected two components, omega 1 plus omega 2 and omega 1 minus omega 2. Nothing wrong here. So these are the desired signals, but we also have some other signals. Because of this 3 omega 2t component, we have some other signals. One is omega 1 plus 3 omega 2, and the other one is omega 1 minus 3 omega 2. Okay, one is omega 1 plus 3 omega 2, the other one is omega 1 minus 3 omega 2, and we will see that the omega 1 minus 3 omega 2, this signal will be very close to the omega 1 plus omega 2 signal. Now for example, if I have omega 1 at 850 megahertz and omega 2 at 900 megahertz, then omega 1 minus 3 omega 2 would be around 1850 megahertz, and omega 1 plus omega 2 is 1750 megahertz. So it's very close to the omega 1 plus omega 2, which is one of the desired signals. And now this component is very difficult to filter out. This is not desired, this omega 1 minus 3 omega 2. It's not desired, and it's close to the desired signal of omega 1 plus omega 2. So this is an undesired signal which is now invaded into our system. Now some of you might be confused as to why omega 1 minus 3 omega 2 is closer to omega 1 plus omega 2. Again, let's go back to our signals and systems class, and we know that the spectrum, right, you can draw it as symmetric, right? So if you have 0, you can draw it omega 1 plus omega 2. There's always minus omega 1 plus omega 2. So you can always draw spectrums as symmetric. To make things simple, for example, let's say this is omega 1 plus omega 2. Let's say this is omega 1, this is omega 2, right? And then this is omega 1 plus omega 2. this is minus omega 1, this is minus omega 2, right? Now if you look at omega 1 minus 3 omega 2, right? So this is omega 1, and you have to subtract 3 omega 2's from it, right? So this is omega 1, this is 1 omega 2, right? So you have to go back 3 omega 2's. So omega 1, so this is 1 omega 2, right? And well, it won't lie exactly at omega 1, but okay, how do we do this? A bit difficult to explain like this. Okay, let me clear the screen and work with numbers. That would be easier. So if I have say omega 1 at 10 megahertz, I can always do, so this is how we represent it, right? 10 as well as minus 10, because from a signals and systems standpoint, they're one and the same. It doesn't matter. Then this is my omega 1, and if this is omega 2, so this is 20 megahertz, right? So this is 20 megahertz, right? Omega 2. Then omega 1 plus omega 2 is 30 megahertz. Omega 1 plus omega 2 is 30 megahertz. This will be omega 1 plus omega 2 minus 30. Now omega 1 minus 3 omega 2 would be 10 minus 3 into 20. 10 minus 60 is minus 50 megahertz. So this is omega 1 minus 3 omega 2. So this eventually lies near omega 1, the reflection of omega 1 plus 3 plus omega 2. It might some people might be confused as to how it comes near omega 1 plus omega 2, but it actually comes near the reflection of omega 1 plus omega 2. In signal systems, we treat them the same, so it eventually we work with their mods. So either you look at this part or you look at this part, it's one and the same, right? And that's how this omega 1 minus 3 omega 2, it comes near the one of the desired signals. Okay, and then it creates problems, because now the system has been designed to work at this frequency, right? So this signal, which is close to the desired signal omega 1 plus omega 2, won't be filtered out, and it will get into the system, and it can create errors